Hello, welcome back to the lesson 2 on vector algebra. In today's tutorial, we are looking at scalar or dot product of vectors. Now, when we say a scalar or dot product of vectors, then we are talking about a way to multiply two vectors and get a scalar or a number as a result. So, when we say a scalar or dot product of two vectors, then we are referring to a way to multiply two vectors and get a number or a scalar as a result. Now, the result is a scalar value that represents the amount of similarity between the two vectors. Now, what are the applications of a scalar or dot product of two vectors? One of the applications of scalar or dot product of two vectors is we use the dot product to find the angle between two vectors. Also, we can use the dot product to find the projection of one vector onto another. And the last aspect that I would like to talk about is in physics, we use scalar or dot product of two vectors to calculate work, energy, and forces in physics problems. For that matter, the dot product of two vectors is a fundamental concept in linear algebra, and it also has numerous applications in physics, engineering, and computer science. Now, let's go to the introduction aspects of this particular tutorial. We are saying that the scalar or dot product results to a scalar or results to a number as a result. In that case, the scalar product of two non-zero vectors, let's say vector A and vector B, assuming that vector A has triple real numbers, let's say A1, B1, C1, and vector B has A2, B2, and C2. Then the dot product of vector A and B is denoted as this. So vector A dot vector B. Now, the definition of a dot product of two vectors, in this case, vector A dot vector B, is defined as we multiply corresponding components or corresponding numbers, which is A1 times A2 plus B1 times B2 plus C1 times C2, and that is what we have here. So A1 times A2 plus B1 times B2 plus C1 times C2, and the result will give us a scalar or a number. The dot product is not a vector, but it's a real number or a scalar, as I said earlier. So when you dot two vectors, the result will not be a vector, but rather a real number or a scalar. So for example, find the dot product of the given two vectors. And then the first vector is vector A and the second one is B. So we know that if you write this vector A in terms of I, J, and K, then we are going to have negative I plus 2J plus 3K for the first one. And then for the second vector, we are going to have 6I plus 5J minus K. Now, if you are to find the dot product of the first question, then the dot product of these two vectors is giving us negative 1 times 6 plus 2 times 5 plus 3 times negative 1. So negative 1 times 6 is negative 6. 2 times 5 is 10. 3 times 1 is negative 3. So negative 3 plus 10 is positive 4. and positive 4 minus 3 gives us 1. So the result of the dot product of these two given vectors results to a number or a scalar, but not a vector. In other case, we have the second question here. So our vectors are 2, our components are 2, negative 3, and this one too is negative 1. So we have negative 1 here. And then the second one, we have b equals, vector b equals negative 1 is here, positive 2, positive 8. And so the dot product between these two vectors is equal to 2 times negative 1 plus negative 3 times 2 plus negative 1 times 8. Now 2 times negative 1 is negative 2. Negative 3 times 2 is negative 6. Negative 1 times 8 is negative 8. So when we sum these three together, we are going to have negative 16 as our final answer. So this is a real number or a scalar, but not a vector. So the dot product of two given vectors results to a number or a scalar, but not a vector. So the solution, of course, is what we have here. And then the result of the second one are shown below. Now let's look at some of the properties of that product. So we are saying that the first property says if you dot two similar vectors or two same vectors, then the dot product between these two vectors, a dot a, gives us magnitude of a all squared. Also, for mutually perpendicular unit vectors I, j, and k, we have it as this: I dot I is equal to j dot j equal to k dot k, which is equal to 1. But I dot j equals j dot k equals k dot I results to 0. We shall talk more about this in the next parts of our lesson here. We are seeing also that the scalar product is commutative, and for that matter, if we dot a to b, is the same as b dot a. So we are saying that the scalar product is commutative. Again, if we have a scalar multiplying a vector dot another vector, then this can also be written as the scalar out a dot b brackets, or we can also move the a out dot the scalar times b, which will result to the same answer. So k times a vector a dot vector b is the same as or is equal to the scalar out a dot b, which is also equal to a out dot k times b. Again, this is also a distributive property of dot product. So a vector a plus vector b dot c gives us a dot c b plus b dot c. Okay. Now let's look at an example. Find the magnitude of a minus b if these two vectors a and b are such that the magnitude of a equals 2 and the magnitude of b equals 3, and the dot product between the two is equal to 4. Now we are saying that if we find the square of these two vectors, the square of the magnitude of these two vectors, then is equal to a dot b, or the expansion form of this one equals. Now let's look at the solution here. A minus b all squared is equal to a minus b dot a minus b, or so a minus b all squared is equal to a minus b in bracket dot a minus b. For that matter, we will dot this one to this, and so we have a dot b. Then we will dot this one to b. So, but there's a minus sign here, so minus a dot b. Another minus sign here, b dot a. And then we have the last one, negative times negative giving us positive. So b dot b gives us this one. But from the first property, we said that a dot a equals to a squared. So the magnitude of a squared. And for that matter, if you dot a to a, you are going to have magnitude of a all squared. And it is b dot b, you are going to have magnitude of b all squared. And so we are going to have magnitude of a squared minus 2a dot b plus b all squared. So when we substitute, we are going to have 2 squared minus 2 times 4 plus 3 squared. So a minus b is equal to root 5. So when we take the square root, then we are going to have 2 squared is 4 minus 2 times 4, which is 8, plus 3, which is 9. So 4 negative 4 plus 9, which is equal to 5. So minus b all squared, taking square root of this one, we are going to have a minus b equals root 5. Okay, so under this example 2, we are saying that if a is a unit vector and x minus a vector x minus vector a dot vector x plus vector a equals 8, then find the magnitude of x vector x. Now we know that if we dot x to x, we are going to have the magnitude of x squared, and then x dot vector x dot this, we are going to have plus x dot a minus a dot x minus, and then vector a dot vector a also gives us a squared. Okay, so now let's check that one here. So exactly what we have here. Okay, but we are saying that if a is a unit vector and then x minus a dot x plus a equals 8, then find this one. So we know that if a is a unit vector, then it means that a is 1. In that case, here we'll cancel this, and we have this one as x squared, but a is 1. So we are going to have minus 1 equals 8. Now, vector x squared, magnitude of vector x squared equals to 8 plus 1. And that magnitude of x squared will be equal to 9. When we take square roots on both sides, we are going to have this one to root 9. And therefore, the magnitude of vector x equals 3. And that is exactly what we have here. So since a is a unit vector, and for unit vectors, the magnitude of a unit vector is equal to 1, or is unity. And also we have this one dot this and equals 8. When we expand, this is what we have. And as I said earlier on, we are going to be left with magnitude of vector x squared minus 1 equals 8. and then magnitude of x squared is equal to 9. Magnitude of x equals 3. Now we are on dot product theorem. The dot product theorem states that if we have an angle theta between two non-zero vectors, let's say a and b, then the dot product between the two vectors equals to the magnitude of vector a times the magnitude of vector b cos theta. So with reference to the dot product theorem, we are seeing that this is if we have a plane, x and y plane, and in the plane we have two vectors, one is here, another one is here. Now the angle between these two vectors is what we are interested at, and this theorem says that the angle between these two non-zero vectors a and b is giving us a dot b equals the magnitude of this one vector a times the magnitude of vector b cos theta. Okay, now let's check this again. By applying the law of cosine to the triangle AOB, so in this case, if we join a line from point vector B, the terminal point of vector B to that of vector A, then we are going to have a triangle. In that case, this triangle, a triangle AOB. And we are saying that in the figure, A minus vector A minus vector B, or the magnitude of vector A minus vector B squared is equal to vector A squared plus vector B squared minus 2 minus 2 times the magnitude of A, the magnitude of B cos theta. So A and B are here. And so if you want to find the magnitude, the subtraction of vector A and B all squared, then the formula is given to you as this one. So in that case, if a question is given, then it's up to you to find the magnitude of the two vectors given to you, and then you substitute into the required formula over here. Alright, for that matter, if we expand this, we know that the expansion of the magnitude of A and B all squared is equal to this one. And when we further expand this, we are going to have vector A times vector A, which is this one. And then this times this is going to be negative A dot B. And then we have another one too, which is also negative A dot B. And for that matter, we are going to have negative 2A dot B. And that is what we have here. And then B, negative B times B to give us positive B for the two vectors here. So we are going to have magnitude of B squared, and that is what we have here. Okay, now we are saying that this is an expansion. This is an expansion of this one. And for that matter, we are going to equate the whole of this to the formula here. And so if we are to divide, then it means that we are going to have, if we are to divide this one, see that this one will cancel this, and this one too. Sorry, if we are to group terms alike, this one will cancel this, and this one too will cancel, and it will be left with this one. And for that matter, we are going to be left with negative 2A dot B equals the rest of this one. Now, if we divide both sides by negative 2, we divide here 2 by negative 2, this one will cancel, and we will be left with the vector A dot vector B equals to this one. So from the dot product theorem, the angle between two non-zero vectors is given by, so when we take cos on both sides, then if we have vector A dot vector B equals magnitude of A, magnitude of B cos theta, then it means that if we are to divide here by cos theta, and here 2 by cos. Sorry, if you are to divide here by magnitude of A, the magnitude of B. So we are going to divide here. So here, so this one will cancel this and we'll be left with cos theta equals the magnitude of, sorry, vector A dot vector B over the magnitude of A and the magnitude of B. Okay, now let's look at an example here. In this example, we are to find the angle between the vectors A and B. And these vectors are given as, we have 1 here. So 1, 1, negative 1. Then we have B2 here, which is also equal to 1, negative 1, 1. Okay, so if you are to find the dot product between the two vectors, then you are going to have 1, 1, negative 1 dot 1, negative 1, 1. And that gives us 1 times 1 plus 1 times negative 1 times plus negative 1 times 1, which gives us 1, negative 1, negative 1. And the final result gives us negative 1. So let's check that one here and see. So that is the result over here. Okay, the next thing is to find the magnitude of the two vectors. So magnitude of A equals, we have the vector in this component 1 squared plus 1 squared plus negative 1 squared. And so we are going to have root 3 as our final answer for this one. So 1 squared is 1 plus 1 plus another negative 1 times 1 is positive 1. Negative 1 times negative 1 is positive 1. So in this case, we are going to have root 3. Now let's find the magnitude of vector B2. And this one, so we are going to have 1 squared plus negative 1 all squared plus 1 squared. And that gives us root 3. So now that we found this, we know that cos theta equals A dot B all on magnitude of A times magnitude of B. And so A dot B gives us, sorry, A dot B gave us negative 1. So we are going to have negative 1 on root 3 times root 3. Okay, so if you check it carefully, this is what you have. This is also the same as negative 1 on root 3 all squared. So we are going to have negative 1 on 3. For that matter, cos theta is equal to negative 1 on 3. And then cos inverse of negative 1 on 3 gives us 109.47, which is 109.47 degrees. So that is how to find the angle between two vectors. Now let's continue to explore more properties of vectors. Now we are seeing that, let's say we have a vector A and B being two non-zero vectors. Then the dot product between the two is 0 if and only if the two vectors are perpendicular to each other. So for perpendicular vectors, if if a vector A is perpendicular to vector B, then we are seeing that the dot product between the two vectors will always result to 0. So let's say this is a vector A, or let me say this is vector A and this is vector B. We are saying that if since these two vectors are perpendicular to each other, then what we are saying is that the dot product between these two vectors will always result to 0. Now, if the angle is also equal to 0, then it means that A dot B will also be result to this one. but the angle is already 0. And for that matter, there will be no angle between. If the angle is 0, it means that there's no angle in between. Then the dot product between the two will always result to this one times this. We know that A dot B is equal to, from our first principle property that we dealt with concerning angles. We said that the formula is given as A dot B equals magnitude of A times magnitude of B cos theta. So if the angle is 0, it means that cos of 0 is 1. And for that matter, 1 times the whole of this will leave us the whole of this as our final result. And that is why we are saying here that if the dot product between the two vectors is 0, then it means that we are going to be left with only A dot B, which is equal to magnitude of A times magnitude of B. Scalar products of collinear vectors. When the vectors A and B are collinear, so we had a vector, there was a vector here, another vector A, B, C. The scalar products of collinear vectors, when the vectors A and B are collinear in the same direction, then we are also saying that the angle is also 0. In that case, we have a collinear vector A, B, C. All this lies in the same direction. Therefore, there is no angle. And that's why we are saying that the angle between two collinear vectors, in this case, we are making use of only two vectors. So the angle between two collinear, let's call this one B, let's call this A. The angle between two collinear vectors is equal to 0. There's no angle in between them. For that matter, the angle between them will also result in the same thing as this. Another one, when the vectors A and B are collinear and are in opposite direction, then the theta is equal to, or the angle between the two vectors will equal to pi, which is also 180. Therefore, we are going to have our dot product between the two vectors as magnitude of A times magnitude of B cos 180 or cos pi. And then cos of 180 is -1. So we are going to have -1 times this times B as our final result for the dot product between the two. Now let's look at an example here. If vector A equals to this and vector B equals to that, we are to show that these two, the addition and then subtraction of these two vectors are perpendicular. Okay, now we said that two vectors are perpendicular when the dot product between the two is it results to 0. So the first thing we have to do is to find vector A plus vector B. So vector A plus, we are going to have 5, -1, -3, plus 1, 3, -5. So for adding corresponding components, we are going to have 6, -2, 6, 2, -8 for the addition. Then the subtraction, we are going to have, so let's subtract. We're going to have 5, -1, -3, minus 1, 3, -5. Okay, so subtracting corresponding components, we are going to have 5 minus 1, and that gives us 4. -1, -3, -4. -3, this one is negative times negative, giving us +5. So -3 will give us +2. So this is the result for the 2. Now we are to show, now let's check that one. Okay, so our A minus B, we had 6 2 negative 8. And this is what we have here, 6 2 negative 8. And we have this one too as 4 negative 4 and 2. And now we are going to have the dot product between the two. So 6 2 negative 8 dot 4 negative 4 2. For that matter, 6 times 4 plus 2 times negative 4 minus 8 times 2. So 4 6 24 negative 8 negative 16. So we are going to have 16. So we are going to have 16 minus 16. 16 minus 16 results to 0. So the result, which is 0, indicates that the two vectors are perpendicular to each other, in a sense that the dot product between the two vectors resulted to 0. Okay, now there's another one that we would like to talk about, which is the component and projection of vectors. Now, the components of a vector A along B, or the components of A in the direction of B, is defined to be magnitude of A cos theta. So when we say components of a vector, then we are talking about the components of a vector along another vector. So when you check this particular part here, there is a vector A here, there is a vector B here. Then we are saying that the components of vector A, so a part of vector A along B, so along B, so of course we are talking about this, is always this one, A, the magnitude of A cos B. The same thing applies, different orientation is being shown here. So we have this one and here too. And we are saying that when you extend the line here and you extend this one too, then the component of A along B is given as this magnitude of A cos theta. Okay, now note that the component of A along B is negative if the angle is greater than 90 degrees but less than or equal to pi. The components of A along B can be computed by using the dot product. So the formula is given as this. When we divide this one, we are going to have the final answer to the final formula to be A dot B over magnitude of B. So therefore, the components of A along B is given by the formula A dot B over magnitude of B. Now let's look at an example here. Let A be equal to 4, 1, 4, negative 2 and B equals negative 2, 1, 5. Find the components of A along B. So we are seeing that the first thing is to find the dot product between the two vectors. For that matter, we are going to have 1 times negative 2. So 1 times negative 2 plus 4 times 1 minus 2 times 5. We're going to have negative 2 plus 4 negative 10. And then here we are going to have 2 minus 10, and that is a negative 8. Let's check that one and see. Okay, so we have our negative 8 here. Then the next thing is to find the magnitude of B. So magnitude of B equals root of negative 2 all squared plus 1 squared plus 5 squared. So 2 times 2 is 4 plus 1 plus 25. We are going to have root 30. So the final answer is negative 8 on root 30. Okay, so that is what you have here. There's another question here. Find the components of the vector A along the vector B. So the same approach follows, and we have our final result as this one too. Now the distributive of scalar products over addition. Now we are saying that if we have two vectors A and B and C be any three vectors, or the dot product of be A and B and C be any three vectors, then A dot brackets open B plus C equals A dot B plus A dot C, distributive property of scalar products over addition. We want to show a small proof here. Now, from the diagram, we know that OA is denoted as vector A, and that is from here to here is O vector A. We have vector OB, so has been denoted, so from here to here is B, and then we have BC also denoted as this one. Alright, now OC, from O to C, if somebody wants to move from O to C, then if the person moves from here to here, then it's the same as the person moving directly from O to C. For that matter, OC is equal to OB plus BC from our first lesson. Therefore, we can say that OC is equal to vector B plus vector C. So adding this vector to this vector gives us the distance from here to here. Okay. Now getting this one done, we also know that OL, now let's check OL here. So OL is a component of B along this vector A, because the whole of this vector O to A is denoted as the small letter A. And for that matter, the component, the OL, we can say this small portion here, OL is a component of B along this vector A from our previous discussion. We can also say that LM, so from L to M here, so the whole of this side too, we can say it's a component of C along A. So that is what we have here. So component of C along A. OM. Now let's check OM. We can therefore see that OM, so the whole of this side from O to M, we will just combine the components of B along A and components of C along A. For that matter, OM will be equal to components of B along C, along A plus components of A, components of C along A. So we will have OM to be components of B plus C all along A. Alright. Now we have that the dot product between these two vectors is equal to the magnitude of A times the components of B along A. And for that matter, components of B along A has been given as OL. And so in place of components of B along A, we place OL here. And therefore, A dot B is equal to magnitude of A times OL. Also, A dot C can be given as the magnitude of A times the components of C along A. And then components of C along A is LM. And for that matter, in place of components of C along A, we can replace it by LM. Now we have A here, we have A here. Now we can pull A out and then put the rest in brackets. So we pull A out and then B plus C will be in brackets. Now we have A here, we pick one. But here we have a component of B along A and components of C along A. Now we can put these two together and say that A dot B plus C equals magnitude of A times component of B plus C all along A, because B plus C are all components along A. And for that matter, magnitude of AOM is equal to magnitude of OL plus LM. Okay, so the components of OM, as we said, OM here is equal to OL plus LM. That's what we are trying to say over here. Okay, and then we have this one too as A dot B plus A dot C. For that matter, if we expand this one, we are going to have hence A dot B plus A dot C. So if it is also minus, then probably we are going to have A dot B minus A dot C. So if it is also minus, then probably we are going to have A dot B minus A dot C. So if it is also minus, then probably we are going to have A dot B minus A dot C. So if it is also minus, then probably we are going to have A dot B minus A dot C. So if it is also minus, then probably we are going to have A dot B minus A dot C. So if it is also minus, then probably we are going to have A dot B minus A dot C. So if it is also minus, then probably we are going to have A dot B minus A dot C. So if it is also minus, then probably we are going to have A dot B minus A dot C. So if it is also minus, then probably we are going to have A dot B minus A dot C. So if it is also minus, then probably we are going to have A dot B minus A dot C. So if it is also minus, then probably we are going to have A dot B minus A dot C. So if it is also minus, then probably we are going to have A dot B minus A dot C. So if it is also minus, then probably we are going to have A dot B minus A dot C. So if it is also minus, then probably we are going to have A dot B minus A dot C. Thank you very much, and don't forget to subscribe to my channel.